In this third example, we want to determine the cable tension in each case in terms of the weight W. When we look at a figure like this, our attention is drawn naturally to two different locations. The first set of locations might be around these upper pulleys that are attached to a ceiling. If we were to isolate these pulleys, it would tell us something about the force required to be exerted by the ceiling on the pulley in order to keep it in equilibrium. We'll come back to this after we determine the tension in the cable, but for future reference, I'm going to refer in each of these cases to this being point D. That will be the center of each upper pulley when we get to that, to looking at that part of the problem. But to address the question at hand, we want to figure out what the tension is in the cable. It's all one continuous cable in each case. We want to determine what the tension in the cable is as a multiple of W. And that suggests drawing our attention to the load itself and looking at free body diagrams based on these isolating surfaces. So if we take a moment to draw the free body diagrams that go with those, we'll get something like what we see below. Note that all three configurations have an x-component equilibrium equation of 0 equals 0, which tells us these weights can swing back and forth in the x direction as they are raised or lowered. In the vertical direction, equilibrium tells us, in the case of A, that T minus W is equal to 0, or that the tension is just equal to the weight. In the case of B, we have 2 times the tension minus the weight is equal to 0, or the tension is equal to half the weight. And in the case of C, we have 4 times the tension minus W equals 0, or the tension is equal to 1/4 of the weight. What this tells us is that wrapping a cable around a pulley many times has the effect of lowering the tension in that cable. As you're walking around campus and looking at any number of construction sites, you might want to take a look at the cranes that are in use. If you take a look at the number of cable segments that extend from a load, let's say, at ground level up to the boom of the crane, you might notice 4 or 6 or 10 or more cable segments. For a given load, this has the effect of reducing the tension that's carried by the cable. For completeness, let's turn our attention now to those upper pulleys attached to the ceiling at points that are labeled D. What do the free body diagrams look like up there, and what does that tell us about the force that's required to be exerted by the ceiling on the pulley in order to keep that in equilibrium? The center of the pulley is unable to move in either the X or Y direction, and so we'll indicate reaction forces in both X and Y at D, and then we're cutting through the cable segments on either side. Our free body diagrams for the upper pulleys in each case A, B, and C now look like this. For X component force equilibrium, we have that the X component reaction force is 0 in each case. The ability to support a force in the X direction means the upper pulleys can't rock or wander in X. Unlike the lower pulleys, they are fixed in space. If we take a look at the Y component force equilibrium equation, we have for case A that dy minus 2t is equal to 0. But from case A, t is equal to w, so dy is 2w. For case B, we also have dy minus 2t equals 0, but in the case of B, the tension is w over 2, so dy is equal to w. And in case C, we have dy minus 5t equals 0, So dy equals 5t, but t was equal to w over 4, and so our result is that dy equals 5 over 4w. While case C produced the greatest reduction in cable tension, the vertical load on the upper support is lowest in case B.